Hello, everybody. So I'm going to talk about a joint work with Philippe, who is here, and Ankur Moitra and John Urschel, who are at MIT in the math department. And by the way, I like this anecdote. John Urschel is a professional football player. He's a very big guy, very strong in football and in mathematics as well. So, okay, I'm going to talk about discrete determinantal point processes. Actually, I should have put a picture, but you can just Google his name and you will see. Okay, so the realization of a discrete DPP can be represented as a finite sequence of binary random variables, but it can also be encoded as subsets, so random subsets. So if you look at the binary sequence, so I have written 4 of them here, as a random vertex of the n-dimensional hypercube. You can also represent it as a subset of the set of integers between 1 and n, where basically you take only the elements corresponding to the 1 coordinates in your sequence of binary random variables. So for DPPs, we'll use the subset representation. So okay, discrete DPPs are actually a probabilistic model to describe correlated Bernoulli random variables. So you probably know Ising models, for example, and this is another one. And this is actually something that a model that features repulsion. And this is why it has been used a lot in many applied fields like machine learning, where you want, for example, to model repulsive interactions between objects or individuals. Or in quantum physics, they are also called fermionic processes when you want to describe behaviors of fermions in some systems. So the definition is the following. So DPP, a discrete DPP, is a random subset Y, such that for any fixed given subset J of your finite space, the probability that you see J in your random subset, in your realization, is equal to the corresponding subdeterminant of some matrix K. And K is a symmetric matrix, and of course you need those subdeterminants here to be probabilities. So those determinants have to be between 0 and 1. And it's sufficient and necessary to assume that all the eigenvalues of K are between 0 and 1. So you can see in the paper, for example, that Kij encodes the repulsion between items I and J. And using the exclusion-inclusion principle, you can actually, from the definition, find the PMF, the probability mass function of the DPP, and it has this formula. So the goal here is to learn the parameter of a DPP. So imagine that you observe independent copies of a DPP, so y1, y2, yn. So each of them, y1 and also y2 and etc., each of them is a random subset of your finite space. So you see them and you want to recover K star. So you assume that K star is the matrix that is unknown, but that rules those realizations. So our approach is maximum likelihood estimation. So computationally, it's a very hard approach, and we address some issues in the paper. But here I'm going to talk about the rates of convergence of the MLE. So even if computationally it's a hard problem, theoretically it's interesting to study the MLE. First, because it actually makes you learn about the structure of the model, and also because it gives you a benchmark of what you can hope to do statistically. So before going to the statistics, let me point out that actually in the model, the matrix K star is not identified. So, because if you remember the definition, the probability measure, the DPP, is actually only defined through the subdeterminants, through the principal minors of the matrix K star. And actually, you can have another another matrix K that gives the same DPP as long as all the principal minors of K are the same as the principal minors of K star. And in particular, as it was shown in a linear algebra paper in 2014, I think by Udding, you can show that it's the same as saying that K is obtained from K star by pre and post multiplying it by some diagonal matrix with plus and minus ones on the diagonal. And actually you can see that this is the same As for example, if you take k star in this form, so you have some values that are positive. So here I only write the signs. So it's the same as choosing some columns and rows and flipping their signs. And this is the same as pre and post multiplying by such a diagonal matrix. So it means in particular that if you want to estimate k star, what you have to do is to estimate the magnitude of the entries and also the sign pattern. And also it means that when you have an estimator k hats, this is a natural way of measuring its error. So you take the Frobenius norm of the difference between k hats and the element in the equivalence class of k star that is the closest to k hats. So, okay, we're doing maximum likelihood estimation. So here is the formula for the log likelihood function. And the MLE is just a maximizer of the log likelihood. And one function that is very important is the expected log likelihood, which is psi, and which is related to the KL divergence between DPPs. And it's actually important to study this because you know that a key quantity is the Fisher information matrix. So, in particular, if the Fisher information matrix is definite, then the MLE will perform at the parametric rate 1 over square root of n. Otherwise, if it's not definite, the log likelihood the expected log likelihood will look like that, and intuitively you see that k star, the log likelihood is too flat, so k star is kind of is weakly identified. So it will be harder to estimate it, and the MLE will perform worse. So, okay, I need to introduce a definition, which we call the determinantal graph associated to k star. So it's a very simple graph, a graph with no weights, with no orientation, on n vertices where you connect two vertices if the corresponding entry in k star is non-zero. And we say that k star is irreducible if and only if the corresponding graph is connected. And for k star to be not irreducible, it actually means, if you think for 1 minute, it means that k star is block diagonal, up to a permutation of some columns and the columns and the rows. So, and by the way, if k star is block diagonal, it means that you can actually decompose your DPP as a union of independent sub-DPPs. So, okay, in the sequel I will write I sim j when I and j are connected in the graph, in the determinantal graph. So the first theorem that we show is that the Fisher information is actually definite, so it's non-degenerate, if and only if k star is irreducible. And as a consequence of that, as a statistical consequence, we show, after checking some technical conditions, that the error of the MLE is parametric. It's of the order n to the 1 over square root of n in probability. And we also get a CLT that is in the paper. But the second theorem is actually that if k star is not necessarily irreducible, we actually compute the null space of the Fisher information, and we show that the Fisher information, so okay, you have this formula here, I will not take too much time on it, but it basically says that if you restrict the Fisher information on the directions on the matrices H that are supported on the blocks of k star, in the case that k star is block diagonal, then it is definite. And in particular, and then for matrices H that are in the null space of the Fisher information, we need to look at what is the order of the first derivative of the log likelihood that no longer cancels, because this will rule the rate of convergence. And we show actually that if you take a direction in the null space, then the third order, of course, vanishes, because you know that k star is a local maximum, but the fourth order no longer vanishes. So as a statistical consequence, the MLE performs in the block diagonal case, performs at the speed n to the negative 1/4. And also, as a byproduct, we get that the MLE, if you restrict the MLE on the block of k star, it performs at the parametric rate. And of course, this is kind of a useless result because you don't know where the blocks are. You don't know the blocks of k star. So, okay, so as a conclusion, we have characterized the rate of convergence of the MLE. And a surprising result is that it only depends on the structure of the graph. And it does, for example, it does not depend on the number of connected components, for example, the number of blocks. So the rate is either n parametric rate, n to the negative 1/2, or n to the negative 1/4. The problem, of course, is that there are some hidden constants that can be arbitrarily large in the dimension capital N, the size of the matrix. For example, we show in an example where G, the matrix has a graph G that is a path graph. And this is actually a very bad case. And in another paper, where we study a method of moments, which is actually very easy to compute actually in a polynomial time, we show that this determinant graph still plays a very important role. And actually we show that the sample complexity of the method of moments is completely determined by what we call the cycle sparsity of the graph, and I will not define it because I want to keep a mystery, so you go read the paper. And thank you for your attention.
So we have time for one quick question as the next speaker prepares.
Let me just check something. So if the hidden matrix is in general position, then the graph is totally connected.
Exactly. Okay. Yes. If K star, so the question, if K star is a generic matrix, then the corresponding graph is connected, and hence you estimate it at the speed n to the negative 1/2.
Okay. Just one quick question also. How do we know how tight these results are? Like in terms of lower bounds, I didn't catch whether.
So no, I mean actually those results are pointwise for any K star, and the constants that are hidden actually we don't know how to compute them except for very specific cases. But in the other paper actually we have some minimax bounds, and in general if you don't assume anything on K star, if you want a minimax lower bound, we have actually a proof that says that the minimax rate is at least n to the negative 1 over 2 times the dimension. So it's very, very slow.
Okay. All right. Thank you.